Right, so question one. Figure one shows the setup for an experiment to determine the specific heat capacity of 300 gram of a liquid. So that's the mass of the liquid, 300 gram. So right away, if you convert that to kilogram, you divide that by 1,000, you get 0.3 kilogram, right? Let's say using an electrical heater. You can see that to supply two electrical supply, that is this iron thing here with a heating coil inside. Now the heater has a power rating of 105 watt, so that is P. This is M, the mass. Right, so we have P 105 and M 0.3. And this is figure one experiment to determine the specific heat capacity of a liquid. Right, that is the liquid inside this container here. Right, we do not know what is the liquid. um, So they say temperature and time data for the liquid in the polystyrene cup, foam cup are shown in the table here. So we have temperature in degrees Celsius and we have time in seconds. So the time is increasing as we measure in the temperature. So every 60 seconds they're measuring the temperature. So basically every minute they're measuring the temperature. Right? They start off with an initial reading of 25.3 at t is equal to 0 seconds. They said to define the term specific heat capacity. The proper definition they go on here is that so we could state it as specific heat capacity. It is a measure of the amount of energy required to increase the temperature of, you have to be specific with the mass, 1 kilogram of material, and you have to be specific with the temperature as well. Right, 1 kilogram of material by 1 Kelvin or 1 degree Celsius. So it is a measure of the amount of energy required to increase the temperature of 1 kilogram of a material by 1 Kelvin. So this here should get to 3 marks because they just said to define it, right? You have to be specific with the amount of mass, which is 1 kilogram. You have to be specific with the temperature, and you have to state, it is a measure of the amount of energy required to increase the temperature of 1 kilogram of a material by 1 Kelvin. Basically, it had to make sense like this, and you had to have the 1 kilogram and the 1 Kelvin. But if you want to guarantee the marks, you could also put the formula. Specific heat capacity, C is equal to heat energy, which is EH, all over mass by change in temperature. Now, if you know this formula, you could define specific heat capacity. So, straight from this formula, this is the amount of energy required to increase the temperature of 1 kilogram of a material by 1 Kelvin, because you have mass at the bottom and you have temperature change at the bottom. So, it's the amount of energy required to increase the temperature of per kilogram of the material per degree Celsius, if you want to say, or per Kelvin. Right, so that's very important to note. Now the unit for specific heat capacity, if you know the unit of energy is joules, and then know the unit for mass is kilogram, and then know the unit for temperature is Kelvin, right? You could just write the unit for specific heat capacity as joule per kilogram per Kelvin. The reason why it's kg to the minus 1, k to the minus 1 because of the law of indices. Since this is in the denominator, when I bring it on top, it will be to the power minus 1. Very important to note. Right? Understand this? So that's that. So that's our 3 marks there. So now let's say part B here. Assuming that all of the electrical energy produced by the heater is transferred to the liquid, and that P is the electrical power of the heater, T is the time duration of the experiment, M is the mass of the liquid, T is the specific heat capacity, delta theta is the increase in temperature or the temperature change of the liquid. Let's say to deduce the formula which represents the heat energy transferred from the heater to the liquid. Well, we have we have electrical energy is equal to increase in thermal energy of liquid, right? I thought I would have fit in one line here. But anyway, so electrical energy is equal to increase in thermal energy, which means heat energy of the liquid. Increase in thermal energy of the liquid, right? So the electrical energy that will simply given by the voltage multiplied by the current of the heater multiplied by the time it has been on. That is equal to the increase in thermal energy, of the liquid. Okay, yeah. That just basically the mass of the liquid multiplied by the specific heat capacity of the liquid multiplied by the change in temperature of the liquid. I put delta theta, right? Um, but we know power is really voltage by current. That is really power, right? P. So we now have P T, which is the power multiplied by the time, is equal to the mass by the specific heat capacity of the liquid in the container multiplied by the change in temperature. So that is basically the formula there. Right? Understand this? So that's that there. They say using the grid provided on page 7, plot a graph of temperature um, versus time. Well, they will be using the data from this table here. Right? So what I did, couldn't really see properly to draw on this. So I use my own graph paper here and I draw my graph. Right? So I just going to run through things that you would be getting marks for, things to look out for. Right? You see this here, time, comma t seconds. Here's your marks for that, for labeling your axis. Right? With the quantity. So you get a mark for that. Right? Similarly here, temperature, comma theta slash degree Celsius. You want to label the y-axis with the quantity and the unit for the quantity. You might get a mark for labeling x and y. You might get 2 marks, one for each. Right. Next thing, you want to have a proper scale. So you see, like every 2 centimeters on my x-axis, I am increasing by 60. Right, increasing by 60. That is what we call a scale. Right, increasing by the same increment, same amount. That is for the x and the y axis. Right, so you have to have a proper scale. Notice I start both at 0, 0. If you start your both axis at 0, 0, you need to put 0, 0 there. You get a mark for that. Right, so that's giveaway marks there. And how much marks this be for a graph? there's give you 8 marks for a graph. So simple things like that. Even if you plot the graph wrong, you're getting marks for label, right? Um, so what I did, every 2 centimeters on my y-axis, I went up 5. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, right? Proper scale. And then I plot my points over here on the graph, right? So I know all these points are correct. So you might get a maximum of 2 to 3 marks for all these points here, more or less, right? And I draw a best fit line. So that is one here to draw a best fit line. Notice that the straight line, all the points are not on the straight line. It don't have to be on the straight line, right? Sometimes none of the point needs to be on the straight line. But we draw a best fit line, right? That compensate for random errors that may have occurred during the experiment, right? So basically you might have a point a little above the line and then you have a point a little below the line. That is to compensate for the so the data points are basically a little scattered, right? So that's why we draw the best fit, right? They never line up perfect on the line, right? So we draw the best fit and we can see that it cuts the y-axis at this point over here, which is 0, 225.3. So that's the y-intercept, right? Notice I put a title as well for my graph, right? So that is where you get your 8 marks for there, right? Understand where you get marks for, right? So yeah, that's basically it for the graph there. Um, Scale, label access, best fit line, plot points properly, put a title, right? Now they say determine the gradient g of the graph. So you need to know is the formula for the gradient of a straight line. So you'll be doing this in maths and physics and probably chemistry and biology and them kind of thing too. Right? So G, I'm gonna say G is the gradient. That gonna be equal to y2 minus y1 all over x2 minus x1. And again, these values here x2, y2, x1, y1, I think from the graph itself, right? So what I did, you have to if your point's not lining up on the graph, you have to read off 2 new points, and the points must be a good distance apart. You know, what the points close to each other. So I chose I create a point over here. I choose this point here, which is this here, 372 and 57.5 basically. And I chose this point here, which is 0, 25.3. Well, you can see this one here. Right? So and you always want to draw your right angle triangle connecting the 2 points like our habit here. Put your little square there as well. Well, this is not a square, but so put the little square there too as well. Right? Indicating the 90-degree angle. So you show how you read off your 2 points and you put the 90-degree triangle there. So I put in the points that I'm using over here. Right? One point is 0, comma 25.3, and the second point could be 12, comma 57.5. Right? What I also like to do, because sometimes you make an X error, you could put what is x1 and y1. So that will be obviously on the first point, and x2, y2 will be on the second point, if you want to put it like that. So therefore your gradient G would be equal, y2 was 57.5 minus y1, which is 25.3, right, divided by x2, which is 12, minus x1, which is 0. Right? So when you work out this in a calculator, you should get something around 0.0866, and this is to 4 decimal places. But I want to write my final answer here to 3 decimal places. I'll put 0.087. And the unit, this is 5 marks. So obviously the way I would assume the way to put your answer for the gradient in terms of its unit. So the gradient G is really change in y all over the change in x. So to get the unit for the gradient, the unit you have on your y-axis was temperature. Instead of changing y, you can put the unit for what you had on your y-axis, which is really degrees Celsius. All over the unit for what you had on your x-axis, which is really time. And the unit would have been seconds. Time is measured in seconds. So you can put the unit for the x-axis, which is seconds here. So the unit will be degrees Celsius per second. S is for second. So S to the minus 1 will be per second. And this is basically your answer. They should guarantee you the 5 marks there. Right? So that is basically it there for the gradient. Understand this? So here now, part E, they say given that G, which is, remember, G is the gradient, is equal to P divided by MC, where M is the mass, P will obviously be the power. Calculate the specific heat capacity C of the liquid. Express your answer in SI units to one significant figure. Well, we know specific heat capacity, the unit will be joules per kilogram per Kelvin, as or per degree Celsius, as I'll just show you. Um, Heat energy is mass by specific heat capacity by changing temperature. So C would be equal to the heat energy divided by the mass by the change in temperature. Right? So you can either put joule per kilogram per Kelvin or joule per kilogram per degrees Celsius. Right? Either or. So let me just do this question here using this formula. So G is equal to P divided by MC. I could write G as a fraction, G over 1. Reason why I do that is because now I could cross multiply. Right? So I have G multiplied by mass by specific heat capacity is equal to the power multiplied by 1, which is just the power. Now if I make C the subject of the formula there, I gotta carry across the G by M, and I gotta divide. Rule and math say that I divide to the opposite I multiply. So the specific heat capacity is equal to the power divided by G, which is the gradient, multiplied by the mass. Now, before I would have went through in the beginning of the question, I would have converted the mass from 300 grams to kilogram one time, 0.3 kilogram. And well, we already had the power in terms of watt, which is 105. Right? So it's just a matter of plugging in those values here now. Right? So instead of P, we're going to have 105. Instead of G, we're going to have 0.087. Instead, well, multiply by instead of M, we're going to have 0.3. Right? So when we work out this here, we should get something around 4,023. And the units gonna be, well, I got right man in terms of degrees Celsius. So joules per kilogram per degrees Celsius, right? But if you put this answer, you might just get 5 marks out of the 6, because they say, yes, we did the SI unit correct, but we didn't write it to one significant figure. Writing this to one significant figure um, would be 4,000 joules per kilogram per degrees Celsius. Because the first significant figure is 4. So if you're writing it to 4 significant figure, you look for the number after 4, which is 0, which means that we do not round off the 4 to 5. So it could just be 4 and then you put 0 for everything else. So 4000, 4,000. Right? So that is the answer to one significant figure there. Understand this? So let's see. Let's say table 2 shows the specific heat capacities of 3 commonly used liquids. Table 2, liquid and the corresponding specific heat capacities. We have liquid cooking oil, specific capacity 1700. For milk, it's 3900. For paraffin, it's 2100. Using the answer calculated in E part 1 and the information in table 2, state the liquid that was most likely used in the experiment. Well, it will be the one with the closest value to what we got in the calculation. And we did get 4,000 joule per kilogram per degree Celsius when we wrote it to one significant figure. The closest value to that there is milk, which is 3,900. So the liquid would be milk. Understand that, right? Last part, state one precaution that the class should take in performing this experiment. Well, to answer these questions, you just always go back to the diagram in the experiment that, look at the apparatus you're using in the experiment. Mhm. Yeah, well, that will work. So you look for any precaution you could apply for using the thermometer. So you want this to be vertically upright. You don't want this bulb over here touching this metal coil, and you don't want it to be touching the inner walls of the container. Right? So it should be below the liquid, fully immersed in the liquid, but it shouldn't be touching the bottom of the liquid. Shouldn't be touching the corner of the container inside. It shouldn't be touching the heating coil. Right? So those are important things to do. Right? Also, when you're reading this, you want to make sure that your eye is at eye level with the measurement that you take. Right? To avoid, and you had to state why you should read it at eye level to avoid which error. Parallax error, right? Is what you're trying to avoid. So you can say ensure to read thermometer, the thermometer, right? Thermometer measurements, because it's more than one measurement you're taking, at eye level, right? And why? To avoid parallax error, right? Also, you want to ensure that the bulb of the thermometer is not touching the base or the inner edges of the cup, as well as the heating coil. You don't want that bulb touching that at all. And ensure that the thermometer is held vertically upright. So this is one here. You could put that one that I have, that I just call out there, where You don't want the bulb touching anything. You don't want it touching the heating coil or the inner walls of the container. Also, you could put to ensure. I'm putting this one since it's short. The thermometer is held vertically upright. So this is just simple precaution you applied for the thermometer. Right? So again, you look at the apparatus you dealing with when you listen to these things. So you're good with everything so far, right?